All right, so we're going to leave the book for right now and then move to the supplement. In the supplement, you'll have a chapter called Quantum Numbers and Electronic Structure. N is discussed in the book, but L and M are not discussed in the book. And so in this supplemental chapter, it talks about the bugle and the magnetic quantum numbers here. So we have the N, the allowed values of N are 1 through infinity, integer values. The allowed values of L, 0, 1, 2, 3, up to a maximum minus 1. The allowed values of M would be minus L plus 1. The L designation tells us the shape, whether it's an S, P, D, F, G, H, I, etc. shape. And then we could just generate it based on, generate this orbital energy level diagram based on the mathematical constraints. So this is a good drawing. I had to compress things here because of space, but basically this is what it's going to look like. In fact, maybe I'll spread it out. We should be able to draw this diagram. When we draw this diagram, the lowest energy is a 1s. What's another way of expressing the 1s orbital? Say 1, 0, 0. And 1, 0, 0, 1s are the same thing. And then there's a big jump up to the 2s, which is 2, 0, 0, 2s. And then there's a small jump to the 2p. We're going to offset the 2p's. We're not going to write the 2p's directly above here because we're going to subdivide this chart into L equals 0 on the left and L equals 1 here. And so the 2p's are going to be slightly higher in energy here. 2, 1, negative 1, 2, 1, 0, 2, 1, 1. Those would correspond to the 2px, 2py, 2pz, depending on what axis is oriented in three-dimensional space. And then there's a jump to the 3s, but not as big as a jump between 1 and 2. The jumps get smaller as the energy levels are converted. This is 3, 0, 0. So when n is equal to 3, L is equal to 0 is okay. When n equals 3, L equals 1 is okay. So we'll have the 3, 1, negative 1, 3, 1, 0, 3, 1, 1. These are the 3x. Okay. I'm going to continue drawing that as we go up. But as we go up, you can see that it starts to get all kind of messy a little bit here. One thing that's a little bit messy is where's the 3D? You know, I go 3s, 3p, where's the 3d? Well, the 3d is actually promoted way up here into the 4s, 4p region. So it goes like this. In fact, it gets higher in energy than 4s. So we jump from the 3p to the 4s in terms of energy to the 3d to the 4p. But if this is the 4p, where's the 4d? Well, the 4d is way up here. And if this is the 4d, where's the 4f? The 4f is up there, way up there. And so this is the way to remember it here. You know, we would go 4s to the 3d to the 4p to the 5s, not the 4d. Okay, that's a little odd because of the way this is. When we look at each individual n value, then we can see here, in this sense, you know, when n equals 1, L equals 0. That's all we're when n equals 2, L is equal to 0, which is S, L equals 1, which is P. When n equals 3, we have 0, 1, and 2 available to the L values. And so for each n value, we have what we call 3 sublevels, or 3 subshells. And so for n equals 1, we only have 1. The L equals 0, 1s orbital. For n equals 2, we have 2 sublevels, the s and the p. For n equals 3, we have 3 sublevels, the s, p, and d, corresponding to 0, 1, and 2. For n equals 4, we have 4 sublevels, the s, the p, the d, the f. This will correspond to 0, 1, 2, and 3 over there. And so based on this pattern, we could figure out, you know, as we get to higher and higher energies, for example, when n equals 10, how many sublevels do we have? ask you sublevels, those are the L values. So when n equals 10, what are my allowed L values? I got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And so 0 to 9, that's 10. So there are going to be 10 sublevels. Equals 10. So for example, 4f, how many orbitals are there in 4f? The pattern there. We saw there are 5 orbitals in a 3D. When we get to the F, how many orbitals? There's 7, yeah. When we get to the F, L is equal to 3. So how many are there? Minus 3, minus 2, minus 1, 0, 1, 2, 3. That's 7 orbitals. When we get to L equals, let's get to L equals 90. How many orbitals are there when L equals 90? When L equals 90, how many orbitals are there? Close. Closer. 181 orbitals. 181 orbitals. That's because there's a simple mathematical pattern. The simple mathematical pattern are, when we look at how many orbitals are there for each L, there's going to be, well, m is equal to minus 1, 0, and 1. And so in other words, there are 2L plus 1 orbitals. 2L. There are other patterns too. For example, when n equals 2, how many total orbitals are there? When n equals 2, how many total orbitals are there? There's 1, 2, 3, 4. When n equals 3, how many total orbitals are there? 1, 2, 3, 4, 5, 6, 7, 8, 9. Do you see a pattern? When n equals 1, how many total orbitals are there? 1. So do you see a mathematical pattern? When n equals 4, how many total orbitals are there? 16. When n equals 10, how many orbitals are there? When n equals 10, there are going to be a total of 100 orbitals. Could you figure them all out? Yeah, you could figure them all out. You know, it wouldn't be hard to figure out. We start off at the 100, 0, and 0, which is called the 100s orbital. You know? And then what's allowed? The 100 would be, you would have the 100, 1, negative 1. You'd have what would come next? 100, 1, 0, and then the 100, 1, 1. These would be the 100 p orbitals. And then what? 102, and then you go on all the way up to the 100. Is 199 99 allowed or forbidden? Is that allowed or forbidden? 199, 99. Is that allowed or forbidden? That's allowed. Wow. Is the 100, 50, 51 allowed or forbidden? Forbidden. That's forbidden. Forbidden based on these mathematical patterns. So there are a lot, but we aren't going to cover all of them. Instead, we're going to look at this. So when we range it by energy level, n, you know, the orbitals get mixed up, kind of. You know, we can see that the higher the L, the higher the energy. So L equals 0, L equals 1, L equals 2. L equals 0, L equals 1, L equals 2, L equals 3. So it's L But then there's some overlap here. And so what we're going to do instead is we're going to break this up into periods or shells. A shell would be a group of closely spaced orbitals in terms of energy. And so the first shell is here. The first shell only has one orbital here. This is the first shell. And so in the first shell, there's one subshell, which is n equals 1 or 1s subshell. In the second shell, this way, the second shell, there are two subshells. There's the S subshell and the P subshell. In the third shell, the 3D get promoted out of the shell. And so there's only 3 subshells in the third shell. The third shell, I have the S subshell and the P subshell. The D subshell gets promoted to the next shell. The next shell is the fourth subshell. The fourth shell, which has the 4S subshell, the 3D subshell, and the 4P subshell. There. And so we're going to look at this in terms of shells. And so here we have the first shell, the second shell, the third shell, the fourth shell. The 4D gets promoted to the next shell, the fifth shell, and the 4F gets promoted to the sixth shell. Do you see that? So we have that. So you should know this to the first 4 shells. So what we're going to do is we're just going to draw this diagram for the first 4 shells. And so I'm going to continue. I got to the third shell here. The first shell here, the second shell here, the third shell here, and the 3D are going to be up in the fourth shell. So let's go ahead and draw that out here. So this is the next orbital is going to be the 4, 0, 0, and the 4s orbital. And then what comes after the 4s? What comes after the 4s is the after the 4s comes the, we have to go back up to the 3D. And so after the 4s comes the 3D. And so what I'm going to do is I have this divided in terms of L. 3D is L equals 2. The M values are going to be -2, -1, 0, 1, and 2. There's 5 orbitals. And so the 3D subshell has 5 orbitals. So this is the 3D subshell with 5 orbitals. There's 5 different shapes. Each individual orbital has 3 unique numbers or an address. So we'll have 3, 2, -2, 3, 2, -1, 3, 2, 0, 3, 2, 1, and 3, 2, 2. And so it goes 4s to 3D, 4s to 3D to 4p. 4p comes next here. The 4p, L equals 1, so there are 3 orbitals, the 4, 1, -1, 4, 1, 0, and 4, 1, 1. So 4p. And that completes the shell. The fourth shell just goes up to the 4p. Here. So we'll see it. First shell, second shell or period, third shell. This way we can build up the entire orbital energy level diagram up to n equals infinity. It's just a mathematical pattern that we just keep filling in on up. Okay, so the NLM defined the orbital. Now, there's one more quantum number beyond N, L, and M, and it's called S, the 4th quantum number. The 4th quantum number is electron spin. Electrons behave like little magnets, a spinning charge. So we can have magnet pointed up or down. So electrons spin. This is spin up. This is spin down. There are only only two possibilities. It can either be, you know, spin up or spin down. Spin up has a number code for that goes into the Schrodinger equation. And so when we get to spin, which we call S, then spin quantum number. If it's spin up, we call it S equals plus 1/2. If it's spin down, S is equal to minus 1/2. These come from the Schrodinger equation. So what this allows us to do is it allows us to place the electrons into this orbital. So normally what we'll try to do is we'll try to start off with the lowest energy, like hydrogen. The hydrogen, if we put the electron